Today we will learn about strong induction. It is another form of mathematical induction. Okay. Remember, in the mathematical induction, we have two steps. The first step was the basis step, which we show that P1 is true, or we may start at any other integer, not necessarily 1. And then we show that for every k, under the assumption that P of k is true, then we use that to show P of k plus 1 is true. So we assumed that the statement is true at some integer k, at arbitrary integer k, and we call this assumption the inductive hypothesis. And then we showed that under this assumption, we can prove that the statement is true for the integer that comes after k, which is k plus 1. So this is the mathematical induction. Now we will learn another form of mathematical induction, which is a strong induction is called. Now, how the strong induction is built, we start again with what we call basis step, and then we prove it is true at 1, same step as for mathematical induction. But here now, in the inductive step, we will show that the statement, we will assume that the statement is true for 1 and 2 and 3 all the way till k. So for a given arbitrary integer k, we assume the statement is true for all integers less than or equal k, for all of them. And then under that assumption, we show that the statement is true for k plus 1. And here we go. This is here called the inductive hypothesis in the form we learned last time. In here, having P of k, assuming P of k to be true, was the inductive hypothesis. Now, in the strong induction form, the inductive hypothesis is assuming that the statement is true for 1, 2, 3, all the way to k. And then we use this assumption and we prove under that assumption that P of k plus 1 is true. So this is the difference between strong induction and the mathematical induction that we learned last time. Okay, so let us use that to prove the fundamental theorem of arithmetic. We have seen it before, but now we prove it using induction. It says for any integer greater than 1, we can factorize it into a product of prime. Then n can be written as a product of prime. Okay, so let's do the proof. Let me use this space. So we're trying to prove this example. Now, okay. Now we will go for the basis step. Okay. Clearly it says greater than 1. So we start with 2. And certainly P of 2 is true. Why? Because 2 itself is a prime. So we started at some point. So factorizing 2, we do no factorization, just 2 itself as a product of primes. So we consider 2 just satisfy that thing. The inductive hypothesis now we need to show that this statement is true for let me do it this way. Let me write it. Given an arbitrary integer k, then we say the following: assume that P1, P2, all the way to Pk are all true. What is P of n here? I can say P of n is this statement, which says that n can be written as a product of primes. So we are assuming that I shall exclude 1 because we are saying greater than 1. We are saying that P of 2, P of 3, P all the way to K are true, which means that we are assuming that all integers less than or equal K, every one of them can be written as a product of primes. Okay? Now, what do we want? We want to use that to show or to prove that P of K plus 1 is true. Which means we want to show that K plus 1 can be written as a product of primes. Okay? Now, again, if we go back here, this is called inductive hypothesis. I used to write it every time at every example. So let me write it again here. This is, and let me just go underline it by red. Okay, this is the inductive hypothesis. Okay, the inductive hypothesis. Okay, now let's go back to prove this. Now, if K plus 1 comes out to be prime, then done, because it is a prime by itself, so we do nothing. Otherwise, which means if K plus 1 is not prime, that means it is composite. That is, K plus 1 is composite integer, which means it must be written as a product of two integers. That is, K plus 1, equals A times B for some integers A and B, each of them is greater than 1. Okay? Good. And I must add that A is less than K, and also B is less than K, right? Because A times B is K plus 1. So we must have both A and B to be less than or equal. We can allow here equals K. Now, we will use the inductive hypothesis on A and B. Now, notice that each of A and B is less than or equal K. And in the inductive hypothesis, we said that every integer which is less than or equal K can be written as a product of primes. Now, I will say by the inductive hypothesis, each of A and B can be written as product of primes. Okay. we have k plus 1 equals a times b. But a itself is a product of primes, b itself is a product of primes, so their multiplication is a product of primes. Therefore, k plus 1 is a product of primes. Good. Now, by the basis step and the inductive step, did I name both of them? The inductive, I should say here, I wrote inductive hypothesis. I should write here the inductive step. And the inductive hypothesis is the statement. But the inductive hypothesis step is the part 2 of the proof. So now by by the basis and inductive steps, the proof is complete. Okay. So this is the first example of using induction, the strong induction. Okay. Sometimes we need to adapt the strong induction. We can adapt the strong induction to handle cases where the inductive steps is valid only for integers greater than a particular integer. Like some statement will hold for integers greater than or equal 10 or greater than or equal 50 or 100, but not less than this. So we can adapt the strong induction to make the proof start with such a thing. Okay, so what I mean here, assume we have an integer b and we want to show that some statement p of n is true for all integers greater than or equal this b. So how we do it using the strong induction, we will say, okay, we will change the basis step by as following. We will say we will show that the statement is true at b and also at b plus 1 and at b plus 2 all the way till b plus j. So I have j integers or j plus 1 integers, which I prove that the statement is true for each one of them. Okay, so this is the basis step. So far, the basis step for us was to prove the statement at one integer. But now here, we are assuming that the basis step is to prove the statement for few integers, for some consecutive integers, starting at some integer b. This will be clear when we see an example. Now, the inductive step is using this assumption, which is assuming the proposition is true for b, b plus 1, b plus 2, all the way till we reach an arbitrary integer k. So we will assume the statement is true for k and every integer less than k, not only for k itself. Remember, when we worked mathematical induction, we just assumed the statement is true for k only, for k itself. Now we are assuming it is true for k and also it is true for every integer less than k. And then we use all these informations to prove that the statement is true for pk plus 1. And therefore, it is true for all integers k greater than or equal b plus g. This will be clear when we work an example. Now we will apply the new form of strong induction on this example. It says that prove that every amount of postage of 12 cents or more can be formed using just 4 cents and 5 cents stamp. Let me make that clear. It says simply show that every integer greater than or equal 12, every integer greater than or equal to 12, which means 12, 13, 14, 15, 16, and so on till infinity, can be obtained as a summation of multiples of 4 and multiples of 5. Okay. In the exercises you will see questions similar to this. So the statement of this example translated to mathematics is what I wrote in black. So every number which is greater than or equal to 12 can be written as copies of 4, multiples of 4 plus multiples of 5. That means every integer greater than or equal to 12 can be written as linear combination of 4 and 5. So let me rewrite that again. That means so it is good to see this statement. Every integer a which is greater than or equal to 12 can be written as a equals x times 4 plus y times 5 with x comma y are integers, positive integers. Or we might allow one of them to be 0. So I will say natural numbers, because as notation we know that the 0 is considered natural number according to the notation of the book we are using. So okay, any integer greater than or equal to 12 can be written as linear combination of 4 and 5. Okay, so to prove that, so let's use the strong induction. So we will start with the paces step. Okay, we will start with the paces step. So let's see. Now notice 12 equals simply 3 times 4. So 12 could be written as copies of 4. 13 equals 2 times 4 plus 5. So 2 copies of 4, 1 copies of 5. 14 equals 1 copy of 4 plus 2 copies of 5. So good. 15 equals 3 copies of 5. Okay. So do we need to go more? Okay, maybe. 16 equals how many copies? 4 copies of 4. 17 equals 3 copies of 4 plus 1 copy of 5. So good. That gives us P12, P13, P14, P15, P16, and P17. All of them, each one of them are true. All of them are true. Agree? So this is what we have done according to the adapted form of strong induction. To prove the basis step is to prove the statement is true, starting at some integer and taking some few integers after that, and prove the statement is true there. Okay? Now we go to the inductive step. Assume K is arbitrary integer and assume that B12, P13 all the way till Pk are all true. So this is the inductive hypothesis. This is the inductive hypothesis that we are going to use. Okay? Now we want to prove the statement is true for k plus 1. Now remember what this means. This means every integer of these can be written as multiples of 4 plus multiples of 5, or multiples of 4 itself, or multiples of 5 itself, or multiples of both, and then we add. Now we want to show the same thing happen for k plus 1. So want P of k plus 1 true. That means want to show that k plus 1 can be written as linear combination. Can be written as, let me say like this, k equals x times 4, k plus 1, plus y times 5. This is what we want. Okay, then we will be done. Okay. Consider k. Okay, so let me explain what I want to do. Now we assumed that the integer k and any integer less than k can be written as multiples of 4 plus multiples of 5. Okay? Now take k plus 1. Start with it. Take 4 out of k plus 1. Subtract 4. Then we get k minus 3. But k minus 3 is less than k. So the hypothesis, the inductive hypothesis applied to it, which means k minus 3 can be written as linear combination of 4 and 5. Let me write that. Consider that k plus 1, I can write it as 4 plus k minus 3. And I want to work with this. How? By the inductive hypothesis and since k minus 3 is less than k, we can find, say, x1, y1 integers, non-negative integers, some of them might be 0, such that what? K minus 3 is a combination of 4 and 5, such that k minus 3 is x1 times 4 plus y1 times 5. Good? And this gives, now add 4 to both sides, we will get k plus 1 equals, now we will add 4 to this, and add 4 to this. So we will get x1 plus 1 times 4 plus y1 times 5. So the x and y we are looking for, these x and y in green. Now we can make them now make x equals x1 because we have x1 in hand, we assumed we have it, and y simply make it just y1. Then k plus 1 simply equals x times 4 plus y times 5. Good? So we proved the statement is true for k plus 1. And we won't be able to do so unless we assume that the statement is true for all integers less than or equal k, because k minus 3 is one of them. Now to formally complete the proof, we will say that by the basis and inductive steps, the statement is true. I mean here p of k, or p of let me use the form we used, p of so let me just stay basic. P of n, P of n is true for n greater than or equal to 12. Okay, so using the strong or the adapted form of the strong induction, we accomplished the proof. Okay, use strong induction to show that every positive integer can be written as a sum of distinct powers of 2. That is the sum of subset of integers of this form. And here it is giving us a hint, which is very helpful. Now, as usual, I will keep saying that understanding the question is the most important step for solving it, and sometimes understanding the question properly is almost all the solution. And I said understanding the question does not necessarily mean you need to read it again and again. No. Drop it on some example. Make example for the question. The question tells you if something happened, then the conclusion. So make an example for that something and see how the conclusion happens for that such example. Okay. Now it says here every positive integer. So let's keep trying. Let's have fun. Every positive integer. What's about the 1? Can I write 1 as, see here, as sum of distinct powers? Can I write the 1 as sum of distinct powers of 2? So powers of 2, it is either 2 to the power 0, 2 to the power 1, 2 to the power 3, 2 to the power 4, 2 to the power 5, and so on. And we know that 2 to the power 1 is 2 to the power 0 is 1. This is 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. 2 to the power 4 is 16. Okay, more. 2 to the power 5 is 32. And so on. Now the exercise says show that any positive integer can be written as summation of these with no repetition. What does it mean by distinct powers? Any positive integer can be written as summation of these without repeating any of them twice. So how about the 3? 3 is 2 to the power 0 plus 2 to the power 1. Good. So we have 1 here, 2, 1, 2, 3, 4. What's about 5? 5 is the summation of 2 to the power 2 plus 2 to the power 1. Good. What's about 7? 7 is summation of 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0. Did I say 2 to the power 1? I mean, when I said 1, I mean 2 to the power 0. Okay. What's about 9? 9 is 2 to the power 2 plus or 9 2 to the power 3 plus 2 to the power 0. That's easier. 2 to the power 3 plus 2 to the power 0. And we said 7, it is 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0. What's about any other integer? Let's have fun. What's about 23? 23 is 2 to the power 4 plus what? So we have 7 left, which is 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0. Okay, so any integer can be written as summation of powers of 2, and these powers are distinct. Okay, so good. Now we believe it. Let's go and prove it using induction. So we will go for the I mean, if you see a question, I would like you to write. Okay, the question says use a strong induction, so I will write that by strong induction. We will go for the paces step. The paces step, we can see that P of 1, P of 2, all the way to P of whatever. We have just seen all of them are true. Okay, now the inductive step, we will assume P of J is true for all J less than or equal K. What is it, K? Where K is an integer, is an arbitrary integer. Okay, so we could see that P of 1, 2, 3, 4 till 8 or more are true. So we can say assume that if K is any integer, if K is any given integer, assume the statement is true for K and for every integer less than K. We are saying assume that K or any integer less than K can be written as distinctive powers of 2. And then we want to show that the integer that comes after K, which is K plus 1, can also be written as distinct power of 2. Okay? So again, these two lines are called inductive. When you work such a method, you must always write where is the inductive hypothesis. You must refer where your inductive hypothesis is, because in the next step you will say by inductive hypothesis. Okay, now again, what we want here, want P of K plus 1 is true, which means P of K plus 1 can be written as summation of distinct powers of 2. Now look at the hints here. Says for the inductive step, separate the cases where K plus 1 is even or it is odd. So separate the cases. Okay, now let's take these cases. Case 1, if K plus 1 is even, let's see what happened. Then k plus 1 over 2 is an integer because k plus 1 is even. And that integer is less than k, right? So I must write it. And k plus 1 over 2 is less than k indeed. So by the inductive hypothesis, k plus 1 over 2 equals 2 to power, say, distinct powers, right? We don't know what they are. So we will say R1 plus 2 to power R2. And all the way till we reach some Rs, with Ri distinct. Agree? So we are using the inductive hypothesis in there. But this gives us, we want to see what happens for k plus 1. Now multiply both sides by 2. What we get? K plus 1 equals, now 2 multiplied by the first part will be 2 to power R1 plus 1, right? Because 2 times 2 to power anything, say x, is, we adding powers, right? 2 times x plus 1. Okay? And same thing, multiply this by the second term, so we get 2 times R2 plus 1, and so on. 2 times Rs plus 1. And since the Ri are all distinct, then Ri plus 1, so we shift them all by 1, so they will stay distinct. Are all distinct. So we got distinct powers. So we are done with the case k plus 1 is even. What's about the other case where k plus 1 is odd? What we do here? What if k plus 1 is odd? Since k plus 1 is odd, then k is even. Agree? Good. Now we will use the inductive hypothesis. By the inductive hypothesis, we can write, this is right, we can write k equals 2 to powers R1 plus 2 to power R2 all the way to power Rs. Now, with each Ri is greater than 0. Why? Since k is even. We want this k to be even. So we cannot, with Ri greater than 0, I must say here distinct, because I don't want to see 1 plus 1 that will give me odd plus odd even. So they are all distinct, okay? Now, because k is even, and all of these are distinct, then I cannot allow one of them to be 0, because if one of them 0, then I get 2 to power 0, which is 1. And the other parts, the other terms, are 2 to power Ri, which is positive. If I allow one of them to be 0, say R1 is 0, then the remaining R's must be positive, because we have distinct powers. That means the remaining terms are all powers, positive powers of 2, which means the remaining terms are all even. So their summation is even. And I assumed R1 is 0, that means 2 to the power R1 is 1, plus something even, I get odd. K gives me K is odd. That's contradiction. So because K is even, I cannot allow that to happen. So every Ri is greater than 0. Now, K plus 1 is this one here. I will just put it here at the beginning. And K is 2 to the power R1, 2 to the power R2, and 2 to the power Rs. And this can be rewritten as 2 to the power 0 plus 2 to the power R1 all the way 2 to the power Rs with Ri greater than 0 and distinct. And then we're done. And I will let you know now, right, by the basis, and okay, I'm writing it, inductive steps, blah blah blah, till the end. Okay.